Hello and welcome to our full paper presentation today on D3, a massive dataset of scholarly metadata for analyzing the state of computer science research. My name is Jan-Philipp Wahle, and in this paper we did a joint collaboration with Terry Ruas, Saif, Mohammad, and Bela, Gipp. We already know that computer science is a very popular and influential research field. It infects many other research fields such as medicine, biology, as we've seen recently with models from OpenAI solving the protein folding problem. And we're affecting basically everything from research up to jobs. I mean, there's a very popular Oxford study where they say more than 47% of all US jobs are at risk to be automated through computerization. And DBLP is the largest collection of articles specifically focused on computer science with more than 6 million entries, and it offers information about authors, venues, access type, whether it's open or restricted. It just misses those crucial semantic information and content about the actual paper, such as like abstracts or bibliographies, citations, affiliations, and so on. And this information is crucial because we want to analyze the content and the impact of works over the citations or the bias using the author's affiliations and so on. So we're motivated by this limitation of DBLP, which we now propose a dataset, the DBLP Discovery Dataset, or D3 for short, that combines metadata from DBLP with additional data from the actual full text. And here we show a simplified version of the dataset retrieval process. So we use links to articles or DOIs to retrieve the full text of entries from DBLP, and then process the articles and merge their data together with DBLP's entries. So doing this for more than 6 million publications is a bit more technical than portrayed here, which is why we implemented a parallel and asynchronous routine. So there's many processes. They're independently sending requests, and then they're not waiting for the retrieval, so they can send a lot of parallel requests. You have to take care not to send too many requests to one domain to not get blocked, and you have to respect the limits of each of the websites like Springer, IEEE, ACL, and so on. But this routine is fault prone and will do that in a quite fast manner and then store everything together with the DBLP entries. It will parse the PDFs. It will extract the information that we need, the abstracts, author names, and so on. And you can also find the details in the paper. It's too much for here to fit the presentation. So D3, the dataset that we propose, offers over 30 unique features, and the main features that we provide are related to publications, authors, venues, and citations. And in this paper that we present, we provide an initial analysis on the volume, on the research activity, topic trends, also collaboration and impact through using the number of citations. And as you can see, many more interesting questions can be derived about computer science research from those features. For example, regarding the content or the location bias or author gender, venues, and many more. So to summarize, we propose the D3 dataset, which has more than 6 million entries and is focused specifically on computer science research. D3 has 32 unique features and has a very lightweight format, is accessible, and we also include abstracts in addition to titles, at least for the openly available papers, to enable a semantic analysis. So our analysis in this paper starts with looking at the volume of computer science research. So here we plot the number of publications in logarithmic scale over the time from 1936 to 2021. In orange, we also plot the number of authors in a linear scale. We observed that computer science research is growing exponentially, and from 1952 to 1962, so in 10 years, the number of annual publications also increased by a factor of 10. Wow, that's a lot. On average, the number of publications is growing 15% annually. If you compare that, for example, by a GDP growth of 2 to 3% a year, or an equity market growth of 5 to 7% in the US, this number is actually really high. As we collected the data set until December 2021, not including the last months of December, we see a slight decrease in the number of publications and authors in 2021. This will be updated in a following release, including the month of December then. Next, we show the total number of authors that have published at least one paper, 2 to 5 papers, 6 to 15, 16 to 100, or more than 100 papers. We find that 45%, or almost half, of all authors published only one paper, while around 20% have published 6 or more papers. And this pattern is quite similar to a study done on an NLP-focused repository, which is the ACL anthology. So LREC is also part of this anthology, and all the ACL events and some other events are part of this anthology. And since we have all the entries from the ACL anthology also here in D3, we can use the dataset in the future to compare those sub-areas like NLP with others such as computer vision and analyze their differences regarding research activity. Next up, we plot the relative amount of authors that have published papers over consecutive years. So imagine we ask the question, how many authors published at least 2 papers in the last 13 years? So that's where the red circle here is. So the result will be 45% or 45.95% of authors published at least 2 papers in the last 13 years. So including time in addition to output enables understanding the research activity and productivity of authors here. We can see that most authors publish up to 2 papers over a time of 13 years, and when reducing the number of years, we'll still have 35.73% of authors who published their 2 papers in 2 years. And assuming that many researchers are actually PhD students, and an average PhD takes around 3 years, it makes sense for the mass to be centered around a rather short time horizon and a limited amount of papers. Many more questions about research activity and productivity can be answered in the future using D3, which will make computer science research more transparent. Using the abstracts as summaries for a paper, we plot here the most common unigrams between ACL 2017 on the y-axis and ACL 2021 on the x-axis, which are both included in the D3 dataset. On the diagonal, we're finding similar terms that are present in both conference years, such as supervised or attention have similar term frequencies between both of the conferences. This is actually expected because supervised learning, also self-supervised learning, is still a popular trend in both years. And attention has been used in LSTMs back then, it's now used also in transformers, so this probably has not changed that much. We clearly also find outliers representing the trends that we perceive in the ACL research, which are terms as BERT or transformer, which of course they don't have any occurrence in 2017. I mean, the transformer was introduced in 2017, and then BERT was introduced in 2018, and then more and more people used it and adapted it to different architectures and tasks. In 2021, the term BERT occurs over 90 research papers in ACL. And this just underlines the model's popularity now. Next, we look at the bibliographies and the citations within D3. There are 2 types of citations. So basically, the incoming citations means how many papers cited the work that we look at. So how many citations did the paper get? And the outgoing is just the number of references in a work, in the bibliography. So the number of references used in bibliographies increased actually quite a lot. So we have a cubic approximation here. In 1960 or before, the papers only used 5 citations on average, while after 1980, the amount doubled to 10 citations. And today, it is even common to have more than 30 references per research paper, which is also something that we see, stating this popular quote, standing on the shoulders of giants. So we're using more and more research that has been done in the past to build the models of the future. So looking at the ingoing citations, which are the citations that an individual paper receives, we observe a linearly approximated decline. The variance in the number of citations before 1980 is high, showing that some years were strong drivers of progress, but especially the time until end of World War II in 1945 has many fluctuations simply because there's a low number of records in general. The decline in average number of citations per paper can originate from an increase in publications, so the volume got higher, but the distribution changed to focus more on specific ones, but mainly is the simple result of papers not having accumulated citations over time. So if you go more further to the right side of the x-axis, you'll just see a decline because those papers are quite new. And in the future, if we had a time-weighted correction, for example, that would have an average per year independent in relation to the accumulated citations, we would reveal better how many citations paper receive on average. So extending this analysis, one could also ask which years are the most relevant for papers to get cited. Like most works, they gain momentum quickly, but they receive most of the citations after many years when the concept is more widely accepted. So the first years are probably not that significant, while the 5 or 10 years would be the ones where they gain the most. So next up here, we also plotted the histogram of incoming, outgoing citations. Most papers receive less than 10 citations, and 30% also receive no citation at all, which is a very high number. Only few papers achieve outstanding amounts of citations, more than 100, which is quite a lot. And the distribution of ingoing citations is skewed to the left, while the outgoings is skewed to the right. So in short, we cite more, but we get cited less on average. This is also reflected by the medians. So the median of ingoing citations is at 8, while the median of outgoing citations is at 18. When looking at the number of authors per paper, we can observe another interesting trend. The number of authors per paper increases with a cubic approximation again. So while before 1960 it was usual to have only 1 or 2 authors per research paper, today in 2021 we have on average 4 authors per paper. So we interpret this as an increase in collaboration and research group size, which is on par with the increased output reflected in the number of publications. In the future, when analyzing affiliations, we could understand which institutions and companies like to collaborate together, and even how collaboration networks form over time. For example, if you meet someone from a different university where you had an internship, and then you start collaborating with that group, and the two groups get closer together, and they maybe even invite a company to join because it's a not only research but industrial-driven project, we could find that out if we look over time which affiliations work together. So this was our first initial analysis of D3, and the focus here was to create the data set and then do a first proof of concept of the features of D3, which we showed here in terms of the volume, research activity, collaboration, and also citations. In the future, we want to make D3 also available through an interactive and open web-based system in which other researchers can answer questions about computer science research. And we're currently developing topic models to understand the influence of research areas within computer science. Like, for example, a question we ask ourselves is how much, in terms of citations, did the transformer model influence computer vision in comparison to NLP? So what we could do is we could take the bibliographies of those papers and we can run a topic model of every paper that cites the transformer paper, and then how is that paper constituted in terms of their citations. So maybe it cites 50% computer vision, 20% reinforcement learning, and another 30% of something else. And we could end up with categorizing a paper into a research area by percentage, and then find out how much that is influenced by the transformer model, or how many papers from that area use the transformer model. And we also want to extend our study to be more specific about the impact, success, and productivity. We showed in this research that there are indicators for research activity, but we left open how to define impact by citations or productivity by the number of papers over time, or even how to define a successful author. So that's also something we want to explore in the next paper. And also we want to raise, of course, the important points of fairness and gender gap in this research project. For example, how many authors have affiliations from first world countries, from developing countries? Can we find out if those are minorities? What about the gender of the authors? Those are all questions that we're asking ourselves now. To give you a small sneak peek, here's a screenshot from the front end that we're currently working on with the basic functionalities from the paper. It's still work in progress, and later we aim to use this tool, or to provide this tool to everyone so they can answer questions like we did with arbitrary queries and filters. So for example, we did a research activity analysis over 13 years. You could do some for 20 years. Or you can show the volume in the last 10 years and compare that to the volume in the years from 1960 to 1970, and so on. So the potential should be quite limitless in this regard. And yeah, this leaves me here to encourage you to explore D3. So check it out. The code and dataset is already available and will always be free for research purposes. And I would also like to thank my co-authors here, Terry, Saif, and Bela, for our joint efforts on crafting this paper. I really had a good time with you, and I really enjoyed this research project. Thanks also to everyone here in the audience for showing interest in our work. I think this dataset has a great potential to make computer science research a little bit more transparent and to answer exciting questions in the future. So I hope to see you in the next paper presentation when we actually present our analysis tool. And thank you so much for listening.